Good afternoon, everyone, and thank you for attending our electrical versus mechanical requirements in Flex and Rigid Flex PCB designs webinar. My name is Ryan Wood, the Content Marketing Manager here at Epic. Before we get started, I just want to let you all know that you'll be muted during the presentation. If you have any questions as we move along, please enter them into the questions panel, which is located in the webinar control panel, and we'll try to get to all of them at the end of the presentation. If we don't have time to go through all your questions, we'll be sure to reply back to you by email. Also, we'll be recording this webinar, and we'll post both the recording and the slides on our website and YouTube channel. Our presenter today is Paul Tomei, our Product Manager of Flex and Rigid Flex Circuits. Paul oversees our entire Flex and Rigid Flex PCB product line. Paul's main responsibility is working with customers on technical support, but he is involved in every project from the beginning design stages to delivery. He works directly with customers on their specific design requirements and make sure that each product is designed correctly while troubleshooting any issues that may arise in the process. Paul came to Epic with 24 years of vast experience in the electronics industry. He's been involved in all aspects of the industry, including sales, engineering, and manufacturing. So without further ado, I will pass it over to Paul.
Thank you, Ryan. Thanks for joining us today, everyone. We appreciate it. As Ryan mentioned, the topic of today's webinar is going to focus on the electrical and the mechanical requirements that you encounter in a flex or rigid flex design and how those two different sets of requirements interact and play with one another. So we've broken the agenda down into three groups. First group is the electrical requirements, and the key items in the electrical requirements are whether controlled impedance is a requirement. If so, what type of configuration the controlled impedance needs to be, whether the design requires EMI shielding, whether the design has any significant current carrying requirements, and the complexity or Gerber layout layer count of the design and what that impact. Second element is the mechanical requirements, and this is going to focus in on the key mechanical requirement. There are some other smaller mechanical requirements, but this is by far the largest one, and that is the minimum bend radius requirements for the design for it to fit within your application. And the applications are broken into three different types. The static application, where the circuit is bent once to fit into the packaging. A dynamic bend motion application, where the flex as a function of the end product's operation, the flexible circuit is in constant motion. And we're also going to touch upon folded flex bends, and we'll get into a little bit more detail on that specifically a little later on. And the last section is, now that we've identified the requirements for both electrical and mechanical, we're now going to review some design options and solutions to address the challenges that arise. So specifically, the challenge. Rigid flex and flex technology ends up creating a very unique combination of both electrical and mechanical requirements combined into one design. And a key element of this is the mechanical and electrical requirements are virtually independent of one another. They exist in two separate worlds, and they have completely separate requirements. And as a byproduct of that, you often create conflicts within the design. To kind of summarize those conflicts, electrical requirements tend to increase the thickness of the flex, while the mechanical bend requirements mandate a thin flex construction so that the part will bend to meet the packaging requirements and do so reliably. And the key element here, as far as the minimum bend, is it will always be a function of the thickness of the final flex circuit. I also want to point out this whole challenge of dealing with both mechanical and electrical requirements probably takes up more than 50% of the conversations we have, 50% of the time in each conversation that we have with our customer when we're working with them in developing or creating the foundation for a new design. It's by far the most important element is how mechanical and electrical interact and combine. And interestingly enough, in the majority of cases, our customers will come into that conversation with the following statements. If it's a static bend, they'll say, oh, it only has to bend once. And if it's a dynamic bend, they'll go, oh, you mean the rules are different? And that's the starting point. So moving on. So let's get into the electrical requirements. So the most common one is controlled impedance. Obviously, controlled impedance is necessary for most high-speed signals to perform properly. And with very few exceptions, achieving controlled impedance in a flex or rigid flex design is easily accomplished. As a general rule, it's going to require thicker than what you would call a standard core thickness in order to achieve the impedance values. And that's as a function of the dielectric constant of the materials and the spacing required between your signal layer and your reference plane. So now we're talking, while a standard core might be 1 mil in thickness, controlled impedance will need a minimum of 2, potentially 3, potentially 4 mils in thickness. So it has a dramatic impact. Higher end controlled impedances, such as 120 ohm differentials and 60 ohm single signals, drive this even further. You require even thicker core thicknesses in order to achieve your controlled impedance. There is an option of a one-layer coplanar configuration, but we rarely see this being applied. Instead of having a separate reference plane underneath your signal layer, you achieve that by having ground lines running parallel to your signals on the signal layer. And we find in most designs it becomes pretty prohibitive because it consumes a lot of space and you end up not having enough real estate to route all of the signals. So now, as a byproduct of controlled impedance, you now have to determine what configuration. And the two most common ones, configuration that you need to utilize in the design. And the two most common configurations are the first, a surface microstrip. And this consists of 2 layers of circuitry, 1 layer containing all of your signals, and a secondary layer acting as a solid, typically a solid ground plane, acting as a reference plane, which in turn allows the impedance value to be generated. The second now is stripline. This is a 3-layer configuration. Your signal layer is sandwiched between 2 reference planes, so there's one above and one below. The advantage of the stripline is you've now also achieved full shielding on your signal traces, which may be a necessity depending upon your EMI and RF requirements. As a comparison, moving from a surface microstrip to a stripline is going to increase the thickness of the design by approximately 60 to 67, around 67% thicker. It's a significant jump. And that's, again, primarily because of, or exclusively because of that second reference plane. And physics also required you to use slightly thicker cores than what you could get away with in a 2-layer signal. So again, controlled impedance and the configuration of the controlled impedance is causing your flex circuit to increase in thickness, in some cases very substantially. Here's an example of a 4-layer rigid flex design, 2 layers of flex in the middle, layers 2 and 3. And the controlled impedance in the flex layer is configured as a surface microstrip. So layer 2 is your signal layer. Your polyimide core is 50 microns or 2 mils, and then you've got a reference plane. And this configuration is very much a standard for 90 ohm differential, 100 ohm differential, 50 ohm single-ended, which are still by far the most common requirements. This example now is the same 100 ohm differential, for example, but in a 3-layer stripline configuration. So obviously we can see that the total stack up increased from 4 layers to 5 layers. We now have 2 reference planes, layers 2 and 3, sandwiching in the middle, layer 3, which is our signal layer. But a key element here is, while previously we had 1 polyimide core at 50 microns or 2 mils, in this case we have 2 layers of 75 micron 3 mil cores plus a layer of adhesive at 25 microns in order to create a stack up that will then provide the 100 ohm differential impedance lines on layer 3. So this is a significant increase in thickness. So moving on to EMI and RF shielding. Obviously a requirement in many designs that have to operate in a noisy environment. And no matter what solution you apply, it requires added external layers to be added to the design. And those layers are then act as the shield, and they are connected to ground. So as a byproduct of adding layers, you're automatically increasing your flux thickness. The options available in the industry are specific EMI shielding films, which are very much the preferred solution, providing that impedance is not required. And we'll get into the details of that in a little bit further on. Adding additional copper layers. It's the solution if controlled impedance is required. The downside is it results in a flux circuit that's 50% thicker than if you were utilizing shielding films. The last option, and I put this here because we still encounter it on occasion, is using silver ink as a shielding layer material. We've talked about silver ink in other marketing blogs that we've done in the past. I'm not going to delve into the detail. I think it's suffice to say that it's becoming very much an old technology. It's not one that we recommend or support anymore. So the EMI is the preferred. If no impedance, copper layers are going to be your solution if you require controlled impedance. So here's an example of the 2-layer flex with shielding films. And the shielding films attach very easily. They are just laminated to the external surface of the part. They make connection to the ground, so they are grounded. They're not folded shielding, floating shield layers. So in this example here, using standard materials, the total flux thickness comes in at about 150 microns, which is equivalent to 0.006 of an inch. So there's still a very high degree of flexibility. Now in our next example, this is the same design, but utilizing copper shield layers. Now the copper shield layers automatically drive the total layer count to 4. In the shielding films are not defined as being an active circuit layer in the design, but in a 4-layer copper shield version, or when utilizing copper shield layers, I should say, they do become active layers in the construction. So our design automatically goes up to 4 layers. We've got 3 internal polyimide adhesiveless cores as opposed to 1. We've got 2 additional layers of adhesive in order to laminate all this together. And to achieve the same level of shielding, the flex circuit is now up at 230 microns, which is approximately 9 thou. So it's increased the thickness of the flex by about 50%, which is, again, in many designs significant. There's also the added element that dealing with 4 layers, this is a more costly construction. It costs more to add the additional copper shield layers than to utilize the EMI shielding film. Our next topic is the current carrying requirements. And higher current carrying requirements, almost without exception, require thicker copper, specifically if the design does not allow you to route wider traces. Accommodating your current carrying requirements, utilizing thinner copper with wider circuits is the preferred solution, but in many cases you don't have enough real estate to accomplish that, which means you have to go to thicker copper. Your copper layers require thicker cover lay adhesives as well in order to be able to bond and encapsulate. The rule of thumb is you need 1 mil of adhesive per ounce of copper thickness in order to achieve a proper encapsulation that will meet IPC specifications. Now, just as an aside, and this one comes up on occasion, where there's a higher current combined with a higher voltage. The voltage is not necessarily a concern in most designs. Polyimide has a very, very high dielectric withstanding. It's in the 6 kilovolts per 1 thou thickness range. So I've yet to encounter a design where the voltage was a concern. The last element here is the general Gerber layout and layer count required for a specific design. And this, in most parts, is always going to be driven by the design complexity combined with limited real estate. So you can't spread things out, you can't go wider. In order to achieve your routing requirements, you have to increase your layer counts. And while we've talked about controlled impedance, we've talked about EMI shielding and higher current carrying requirements, this is the #1 requirement that's going to drive up the thickness of the flex circuit. And in our 2 examples here, we can see a 2-layer construction, standard materials, approximately 6 thou. 3-layer using the same standard materials, we're up in the 9 thou range, or 230 microns. The 3 layers are going to require also additional adhesive layers in order to bond the multiple layers together. So as a rule of thumb, the 3-layer is going to drive your thickness up by about 40%. So having covered all of that, we now have to tie all of those electrical requirements and their inherent need to increase the flex thickness with the mechanical requirements. So the first consideration is what sort of application? Is this a static or a dynamic application? For a static, or what's referred to in the industry as a bend-to-fit application, again, general rule of thumb is up to 5 layers maximum recommended. There's some challenges that occur when you start getting beyond that. The biggest one is that you significantly detract from the bend capability. While it is referred to as a bend once to fit or a bend to fit, you can actually, in most applications, manipulate the design in the 10 to 20x range in order to accommodate the assembly procedure, potential future servicing. Bend to fit designs are definitely controlled impedance, definitely capable of carrying higher currents, and there are also EMI shielding options available for all of them. In the next application, it's the dynamic application. You're looking at a flex design that is going to be bent and unbent over potentially an infinite number of cycles. And the example we're showing here is the flex ribbon cable that's used to connect the print head within a inkjet printer, which is probably the most ubiquitous or most common application. Per IPC guidelines, they strongly recommend that it's limited to a one-layer construction. 2 layers can be used, but you need to start to utilize some of the more thinner materials that are available. You also need to utilize rolled annealed copper, which has a higher degree of ductility and reliability when bent. Dynamic applications are not suitable for controlled impedance or high current. The impact that controlled impedance and high current have on the thickness of the design, in the vast majority of cases, will not meet the bend requirements. Now, one of the challenges with a dynamic application is that IPC does not define a less than infinite number of bend cycle applications. So we tend to go from one extreme to the other, which is the one-time bend to fit application, all the way to the other end of the spectrum, which is the infinite number of bends. Now, if you have a design where there is a predefined number of bend cycles, be it either 100, 1,000, 10,000, then the rules obviously do change a bit, but they do tend to come back to having to prove out the design with in-house testing as part of the prototyping process. So here's an example. This is the minimum bend radius requirements as defined by IPC's 2223 design standard. And they're referred to it as an estimation formula. It's I've got the section listed there. And it's an equation that's been based on the maximum allowable copper elongation and the material thicknesses in a given design. It's a little on the complicated side. You can see from the formula beside. You also have to apply the correct copper elongation percentage. So there's a number of variables, and it tends to be cumbersome. The industry, for the most part, runs on has rules of thumb for what your minimum bend radius can be for a given construction. So, for example, a static. In a one-layer design, you can routinely go down to 6 times the flex thickness without any concerns. What does that mean? If your flex is 5 thou thick, then your minimum bend radius is going to be 6 times that, 30 thou. One-layer design has the inherent advantage that the copper is actually right in the middle of the construction, as you can see, as is represented in the image, and it allows for a tighter bend. 2-layer designs, typically in the 10 to 12x range. 3-layer plus designs, 15x plus. And again, with some exceptions, a 4-layer would be approximately 20 to 25x. A 5-layer would be 25 to 35x. You really have to take into account the material thicknesses when you get into that level and the copper weights. So there's a number of variables that come into play. So the rule of thumb for a dynamic application, again, per IPC 2223, is for a 1-layer, which is the preferred, the minimum bend radius has to be 100 times the flex thickness. So again, if we've got that same example of 4 thou, if we have a 4 thou thick flex design, then your minimum bend radius is going to be 400 thou, or 4/10 of an inch. 2 layers again is an option, but it is the maximum. You don't, you go beyond 2 layers, it becomes extremely limited. Your minimum bend radius now becomes 150 times your flex thickness. The last application is what's known as a folded flex. And a folded flex essentially has a 0 bend radius. The flex is actually folded back on itself and in most cases creased. The benefit of this type of folding or this type of application is it allows you to construct a straight flex circuit and then create bends in it by folding it over in a 45-degree example, as you can see in this image. Excuse me. Again, a one-layer construction is preferred. This is approved and allowed by IPC 2223 design standard. Two-layer configuration is capable. Again, you might need to make the provision to use thinner than standard flex cores. If controlled impedance is required, you can only do a coplanar. If you were to try and implement either a stripline or a microstrip, your flex thickness becomes way too big in order to reliably withstand the folded. It is, without exception, a one-time and one-time only bend. When you bend it, the copper within the circuitry layers becomes deformed and elongated as a metal. It starts to work harden and embrittle. It hasn't broken, it's still fully intact, but it has lost a significant amount of its ductility. So if you were to open it again, that's when the problems happen, is that further manipulation is what causes the breakage in the circuitry. A common preventative measure or safety measure is to add a small piece of PSA or double-sided tape at the fold location to retain the fold and prevent it from being opened up. So we've got our electrical, before we get into the design solutions, just to summarize a little bit, we've got our electrical requirements, some of which inherently drive up the thickness of the flex circuit. And then we've got our mechanical requirements that in order to meet a bend requirement, we need to keep the flex circuit as thin as possible. So the electrical requirements and the mechanical requirements tend to be very much mutually exclusive. And when you combine them, they don't always like to play well together. So for design solutions, this is one of the areas that we see creating the larger challenges between the electrical and the mechanical requirements is integration. And we've seen many occasions where where a customer is trying to achieve the highest possible degree of integration within a given design, which is a lofty goal and a righteous goal in most cases. However, we have seen many cases where excessive integration creates a significant amount of design challenges. Specifically, because of the high level of integration, there's a larger degree of interconnects required, limited real estate in the size and shape of the part. That inherently is going to drive up the layer count in order to achieve the routing requirements. And just tying that back into our previous section, increased layer counts is the number one aspect that creates the largest challenges by having the largest impact on on increasing the thickness of the flex. And with today's designs, given the technology of today's products, controlled impedance for high-speed signals is very much a common requirement, as well as power distribution throughout the finished design. So we now have that combination of both impedance control and current carrying requirements. What we've been able to accomplish in many cases is taking a step back from a fully integrated design and entertaining what a multiple part configuration will allow us to achieve. A common scenario would be to utilize a separate add-on flex for specific requirements, be it either controlled impedance or the higher current carrying signals, rather than having that integrated into the design. The general benefit that comes from this multiple part configuration is that you're now working to, you now allow yourself to reduce the flex thickness or flex thicknesses in the design, which then comes back and improves your minimum bend capabilities. There's also a slightly added benefit in many cases where the individual parts become more simplified. Rather than having one very large complex entity, you've got 2 or 3, maybe 4 individual but much simplified entities. And in some cases, that also works to drive a considerable amount of cost out of the design. Moving on into the Gerber layout, some of these things, if you have experience in laying out in rigid board layout, some of these things are going to be pretty straightforward. Because in a flex circuit, your preference is to use thinner copper. Thinner copper equals a thinner flex equals a tighter bend radius. You also want to take advantage of the reduced line widths and spacings that you can achieve with that thinner copper. So as a comparison, half-ounce copper in a production environment, we can routinely go down to 3.5 thou line in space. While if you're working with 1 ounce copper, you need to be up in the 5 thou or greater line in space. So that's going to free up some real estate, potentially allow you to achieve a tighter or a higher density routing package, and potentially minimize the number of layers that you need to use within the design. Another trick, and this is specific to flex circuits, really doesn't do anything in a rigid board, is offsetting the circuits as they exist, as they're routed between adjacent layers within the design. I've got a little example here in the bottom left-hand corner. This is taking advantage of the fact that the polyimide core itself is flexible. And within a design, that polyimide core will move, will bend within the design. So by having your circuits offset from one another, it allows the polyimide core to essentially serpentine between adjacent layers, allows them to package a little tighter. And this occurs specifically when you're bending it. When it's laying flat, this scenario doesn't occur. It's when you're bending it and getting close to the minimum bend radius capability. So again, this is something that we recommend if the design allows. Some don't, because you've got such a high density of circuit routing that you can't offset them from one another. But it's something that should be attempted, at least in the early renditions of a layout. And the last item here is reduced layer count. And obviously that's what we're trying to achieve. But specifically in flex and rigid flex designs, your flex layers, odd layer counts are manufacturable and allowable. In the rigid board world, we tend to work in even layer counts, 2, 4, 6, 8, 10. In rigid flex, it's very easy to have, it's very common to have for example, a 5-layer rigid with 3 layers of flex construction. So you don't automatically have to go to an even layer count. Another element is the actual stack-up, how the part is constructed. This is a very common solution. It does have some limitations, but it's extremely commonly used. So in this example, we're looking at an 8-layer design that actually has 4 layers of flex circuit. Now, the 4 layers of flex are not laminated together into one 4-layer thick entity. They're configured in what's referred to in the industry as an air gap construction. So in an air gap construction, you take those 4 layers and you split them into 2 pairs of 2. And those 2 pairs of 2 exist independent from one another in the construction of the finished part. The significant benefit of this is that when you're bending this design, your minimum bend radius is based upon a layer pair and not the entire 4 layers structure. The flex layers are bending independent of one another, so that basically halves your minimum bend radius, if not more. So again, to summarize, the minimum bend capability is based on the individual layer set thickness and not the total of all of the flex layers. So this is a significant element or a significant option. And material selection, I just wanted to touch upon this quickly. There are 2 types of material available. In the example on the right-hand side, the upper one is your traditional polyimide or flex core material. The copper is attached to your central polyimide core by means of 2 layers of adhesive. And then there's the more recent one, the next construction down, also referred to as adhesiveless, where the copper is cast or attached directly onto the polyimide core without the need of any adhesive. You can see inherently it reduces the thickness of the material. Reduced material thickness results in improved bend capability. Thinner materials. Polyimide materials are available down into the 1/2 mil range. Not 100% standard, but they are getting pretty common these days. You can also do that in cover lays. Again, utilizing thinner materials, thinner flex, better bend. And the last item is the copper type, and this is almost without exception. For designs that have tight bend requirements or have challenges between the electrical and the mechanical requirements, you have to use rolled annealed copper. The grain structure of rolled annealed copper is elongated, and rather than being elongated and horizontal, rather than being vertically oriented, and it does improve the bend capabilities over your standard electrodeposited copper. So to summarize, and I pointed this out earlier, the combination of electrical and mechanical requirements create most of the challenges that we encounter today working with customers, assisting them in developing their designs. The application that the customer has is going to define basically which solutions are available to help us resolve those conflicts and create a design that is both meets their functional requirements as well as the mechanical and the reliability requirements of being bent. Without a doubt, the individual requirements, be them either electrical or mechanical, often or almost without exception, interact with one another and compound each other. We strongly suggest to our customers, and we provide this support on a very regular basis, to give us the opportunity to review the requirements at an early design stage. That'll give us an opportunity to identify areas of conflict and challenge, gives us an opportunity to provide potential solutions, which in turn will streamline the design process for our customers, with the ultimate goal of ensuring that the design is both manufacturable and meets all of the customer's design requirements.
Thank you, Paul. While Paul reviews the questions that came in, I wanted to briefly mention some of the additional PCB-based products we offer here at EPIC. Custom battery packs, flex and rigid flex PCBs, cable assemblies, printed circuit boards, CNC machining, high reliability user interfaces, flexible heaters, and our energy efficient fans and motors. Next slide, please. All right, so without further ado, I'll return it back over to Paul to get to those questions that came in.
Thank you, Ryan. Actually, we've received quite a few questions. Unfortunately, we don't we're not going to consume an excessive amount of time and try to answer them all in this webinar, but be rest assured that we will respond back to all of the individuals that submitted questions. So from quickly scanning the questions I received, I picked out a couple that are pretty relevant. One customer asks regarding EMI shielding, if a existing silver ink design excuse me, can be converted to take advantage of the modern technology of EMI shielding. And the answer to that is almost an unqualified yes. We've done many, many designs that started off or existed as EMI or silver ink shielded designs and converted them over to EMI shielding film configurations, which provided the benefit to the customer of improved mechanical bend reliability because of the thinner construction, and also reduced cost. Second question refers to controlled impedance. And given that achieving controlled impedance requires very specific dielectric thicknesses within the design, which then contribute to the thickness of the design, can controlled impedance be achieved by using thinner copper, thinner line widths, and thinner flex cores? And the challenge there is that there aren't any material thicknesses available that allow you to create a manufacturable construction. So, for example, 100 ohm differential, half-ounce copper, 2-layer stripline surface microstrip configuration utilizes a 2 mil core. The next smaller, thinner core thickness is 1 mil. There's nothing between 1 and 2, unless you get into special order materials, obviously. But your standard goes from 2 mil down to 1 mil. Now, if you were to try to use that 1 mil configuration, or 1 mil thick core, you would have to use 1/3 ounce copper or even 1/4 ounce copper, and your line width would become less than 2 thou. That puts you now at a very, very high level of technology. Your supply chain becomes minimized. You've added a tremendous amount of expense to the design. So in most cases, not a practical solution. As I said, we've got many, many other questions. We will answer all of them. We appreciate your time today, and we thank you for attending. Thank you very much.